Hello, today we want to practice how we can use MATLAB in order to solve a system of ODE equations. So, actually, let's start with a simple example that, uh, for example, we are a junior engineer at ABC company, and we are asked to, a senior chemist asked us to determine that compound C can be, we know that compound C can be produced from compounds A and B according to the following rate law. And then, unfortunately, at the reactor condition, um, compound C is eventually breaks down to compound D. And senior chemist has determined the kinetic that this occurs at as the following. It is already known that the condition of the process, a fluid can be quickly reduced to the state that effectively stabilizes compound C so that no more D is produced. So we know that the fluid concentration of compound C is the final concentration of compound C. Your boss tells you that the company has recently purchased 110 cubic meter pilot vessel to test the reaction, and she also tells you that they got a good deal, and they got a 1 molar stock drum of compound A and B. Before bringing the reactor online, she would like you to to solve it and give an idea that how long it will take to to reach the optimal, which is the steady state, in order to produce the component C. And we start the reactor as cold condition, means that initially no reagent exists or present, and we want to see what impact the flows of component A and B have on the final concentration of component C. So we need to assume we have some assumption as perfect mixing or constant properties and negligible vapor loss and constant stream density. And then based on the mass balance, equation conservation of mass on compounds A, B, C, and D, we will have the following system of ODEs. And this is nothing but accumulation is equal to inlet minus outlet plus generation or annihilation. So we have these 4 equations. In order to solve it in MATLAB, we know that first we have to go and open a new script. So if we go to the home and we click on the new script, one of these pages, like empty, will be open. So I will click a new script, and you see here there is a page without any name, like untitled, will be open. So in order to save this, I will go to Editor tab, and I click the Save button, Save or Save As, and I can save it with a name that I like. So I cancel this because I already generated 2 of these scripts, and I wrote the code, body of the code, inside it that I want to explain to you. The most important thing is that the subfunction that is related to the that function that we will later on use in the ODE45 would be the same name as the function. This is important that we should consider. Okay, so after we open the new file and we change the name of the function, name of this file to the name of the function, okay, so in this function we define some parameters that we have. Parameters that we know is the volume of the reactor, that is 1000 liter. We change everything to the liter and mole and second. We have first rate constant of the reaction. We have second rate, rate constant of the second reaction, and we have rate of the compound A that is coming to the reactor in the feed, and we have rate of compound B that is coming to the reactor through the inlet. We have concentration of compound A in the inlet, and inlet concentration of compound B also. And then for the volume out, or total flow rate of the system, we sum the amount of the rate of compounds A and B that are coming to the system, because these are only the two compounds that are coming to the reactor. We also define the states that we have. States are variables that we want to calculate them. We cannot measure them, and these are nothing but concentration of compound A and concentration of compound B, C, and D. But since we are defining Y as the array, so the first component of Y, the array, is our concentration of compound A, and the second one, concentration of compound B. The third component of Y is concentration of compound C, and the last one, concentration of compound D. Then later on is the time to write the system of ODEs that we have, and is nothing but the one that is already, we have a red rectangular around it. So we know that in the function we have a dy that shows the output. So we have dy that has actually is like an array. It has 4 components, and we define these equations, and then we will use it later on for the ODE. So the second tab that we have is nothing but the function ODE that will solve the system of ordinary differential equation using the ode45, which is a accurate solver for the system of ODEs. And then there is in order to use the ODE, we need actually arguments, 3 arguments that is coming to the system, and it spits out the final simulation time point and also the state trajectories. The syntax for calling ODE is T out, Y out equal to ODE, and we have to call the name of the subfunction that gives us the equation, and with @ sign we call it here. Here shows us the time range, so it's T0 to T final, and here shows our initial conditions that we have. So T out are the integration time points used by ODE, and Y out is a matrix containing the simulated states at each time instant in T out. And we should not forget to put the symbol @ sign before the name, and T0 and T final are the start and end time of the numerical simulation, and Y0 is the vector containing the initial conditions. That right now is 0 because we are starting the reactor at cold condition. To access the final result, we know that MATLAB provides the state Y out that has 4 columns. So with column 1 contains the simulation result for the concentration of compound A. Column 2 contains the simulation result for compound B. Column 3 has the simulation result for the compound C, and column 4 actually contains the simulation result for compound D. And then if we go to the editor and we press the run button here, we will see that the result will show up in a figure, and this is the plots that shows that how concentration of component A is propagating through the column, through the reactor, and as expected. And also component B, the concentration is increasing because we have some feed, concentration in the feed that is coming to the system, and then later on stabilizes concentration of C and concentration of compound D. So actually After I define this option for the ODE, this shows the tolerance that we have. We increase the tolerance in order to increase the stability of the simulation. And then later on for the plot, we actually plot the V out, the first column, the second column, the third and fourth, in order to find the propagation of concentration through this time, integrating time, and we label it. So Y has the label that we already mentioned, mole per liter, and then for X label we have time second, as you can see here, and then we have a legend that shows each of the components that we have that is related to each of these Y's. So Y out, well, first column shows component A, as you can see in this plot. Yeah, exactly, compound A is here, so it's tagged for us. Compound B is the second column and it's tagged here. So this is the results that we have. Thank you for your attention.